This is chapter 12 of Maguire's book, and we're going to discuss perturbations to the hydrogen atom and exemplify the addition of angular momenta, and also practice a little bit of the application of degenerate perturbation theory. Now we know that for the simple hydrogen atom, the Hamiltonian is given by P square over 2m minus E square over 4 pi epsilon naught r. So this is the kinetic energy term, this is the potential energy term, P square over 2m plus Vr in other words. Okay. We also know that the eigenstates of this Hamiltonian they are well known and they are given by E n naught, and they are really proportional to minus 1 over n squared, and they are given by minus 13.6 over n squared electron volts. Alright. So these are the stationary states of the hydrogen atom. So you solve the shooting very quickly to get these energy levels. We've also noticed that this Hamiltonian can also be written as a radial part Pr square over 2m plus L square, where this is the square of the angular momentum operator, plus Vr. This is something we've already seen when we were discussing the angular momentum in 3 dimensions. Now the eigenstates of this Hamiltonian are labeled as n, L, ml. Correct? So the Hamiltonian acts on these eigenstates to give us the energies E n naught, n, L, ml. Okay. So far, so good. Now, what we would like to do is the following. There are certain corrections to these energies. The Hamiltonian, the nominal Hamiltonian is this parallel Hamiltonian, but there are certain corrections that one needs to make. And there is a whole hierarchy of corrections that are required. So let's call these energies the Coulombic energies. Or the ground state energies. Now, they are called the Coulombic energies because this is a Coulombic Hamiltonian. This is a spherically symmetric potential, and it gives rise to the it comes out of the Coulombic interaction between the electron and the proton. Now, there is a hierarchy of corrections that needs to be made. The first correction that needs to be made is called the relativistic correction. Now, the relativistic correction means that the electron is revolving at high speed, so its energy is modified depending upon the speed. There's another class of correction in the same category is the spin orbit interaction. That is, the electron also has a spin, and the spin angular momentum couples with the orbital angular momentum to give a new total angular momentum. And this is what we would like to focus upon as an example of the addition of angular momentum. So both of these corrections, they lead to what is called the fine structure of the hydrogen atom. Now, in addition to these corrections, there could also be the interaction. There is in fact the interaction of the angular momentum of the electron with the angular momentum of the nucleus, which is the proton. This is called the hyperfine interaction. And we've already discussed in detail the hyperfine interaction. However, we talked about the spin of an electron and the spin of a proton. We did not talk about the orbital angular momentum of the electron. So, this is the entire scheme of interactions that happen at various scales. And there are other interactions which are more complicated. For example, here we could have the lamp shift. Here we could have the lamp shift, which is another interaction. So all of these interactions modify the energy levels that we have found out for the hydrogen atom. Okay. Or on top of that, we can apply a strong or a weak magnetic field to the hydrogen atom. So the hydrogen atom can be inside a magnetic field, as it happens in the universe. There's 97-98% of hydrogen in the universe, and it's seeing a big magnetic fields. So the magnetic field adds an additional perturbative Hamiltonian, and these energy eigenvalues can shift from their ground state energies. Now, if you look at the ground state energies E and naught, we've already derived what those energies are. We've seen them in the modern physics course, etc. And these energies are given in the following form: E and naught is equal to minus 1 over n squared n c squared over 2 into alpha squared. Alright. Now m is the mass of the electron, c is the speed of light, and alpha is a constant that appears frequently in atomic physics or quantum mechanics, and its value is given by E squared over 4 pi epsilon naught h bar c. Right. This is alpha. So you put this value in here, you get the ground state energies. Okay. So the c square is cancelled out actually with this c square. But this is the general formula for the ground state Coulombic energy of a hydrogen atom that's not seeing any additional perturbation. You solve the Schrödinger equation, these are the energies that you get. Okay, correct? And you also know that if you look at these ground state energies, if you put them in the position space, they are just R and M, the radial wave function plus the spherical harmonics. Okay, so all of this is basically what we've already seen in our quantum mechanics course. Now these energies which are derived by solving the Schrödinger equation are given by this. This constant has a rough value of 1 over 137. This is something you should remember. It's such an important constant in atomic physics. It's called the fine structure constant. So these are really the unperturbed energies for the hydrogen. And multiply this by alpha squared, then you get the unstructured energies. So the unstructured energies are alpha squared times smaller than the Coulombic energies. So they would depend upon alpha is got 4. And if you have the hyperfine interaction, then these interactions are order of alpha into the mass of the electron divided by the mass of the proton times smaller than the fine structure energies. Okay? So if these energies are of the order of electron volts, these energies can be of the order of micro electron volts, and these energies are even smaller. Okay? So there's a hierarchy of energy scale. The Coulombic energies are the biggest energies, and these are small perturbations on top of the Coulombic energies. These are even small perturbations on top of the fine structure energies. Now what we would like to do is, we would like to apply perturbation theory and find out the effect of these perturbative Hamiltonians to the fine structure, to the Coulombic energies. Okay. And then so this is the scheme we would like to follow, and then we would see what happens if you apply a magnetic field. So I'm doing this exercise as a part of the addition of angular momentum, and I'm doing this exercise because it is a really nice example of how angular momentums add and how degenerate perturbation theories are created. Okay? Let's first talk about the relativistic correction. And you've already seen the spin-orbit interaction in the recitation. I'll go over it quickly again. Right? देखा ना spin-orbit interaction recitation. तफसील से देखा. उसकी देखी फाइन स्ट्रक्चर एनर्जीज निकालनी. आपकी ये नोटबुक में देख सकते हो इसकी जरा recitation में we know that the energy of a particle, the total energy of a particle is given by mc squared plus pc squared under root. Right? This is the relativistic energy of a particle. ये देखा आपने मॉडर्न फिजिक्स में देखा होगा. अच्छा, very बुनियादी तौर पे the energy of a particle can be written as a triangle. This is mc squared. This is the rest mass energy, and this is the this is the energy, the relativistic momentum, and this is the total energy. It's just the length of this hypotenuse. Alright. Now, if I look at this expression, so far relativistic effects have been ignored in deriving the economic energies. Now, if you look at this energy value, it's really m squared c squared plus pc whole squared under root. Okay. I would like to write this as mc squared 1 plus pc over mc squared and all of this under root. I get mc squared 1 plus piece over mc whole square half. Okay. So this is the energy. Okay. And this is an exact expression. The energy of the electron inside the hydrogen atom is given like this. Now let's expand this binomial. This will become mc squared 1 plus half p squared over m squared c squared plus, let's look at another term. Half minus 1 is minus half. The square of this becomes p over mc raised to power 4 to 1 over 2 plus additional higher order terms. So this is just a binomial expansion. This becomes mc squared plus p squared over 2m plus, in fact with a minus, p4 n over n cube mc squared and an 8 2 4 8 plus higher order terms. So this is the real energy of a particle. Now if you look at these terms, mc squared is just the rest mass energy of the electron. The rest mass energy of the electron can be ignored from all calculations because it just gives a baseline to the energies. The electron is always there, its rest mass energy is always there. So it just gives a datum level for the energy. So it does not matter. Now we would like to see when we write the Hamiltonian for the system. This Hamiltonian, does it properly reflect the relativistic effects? Okay. Now this mc squared is not included in the Hamiltonian H0, but it does not matter because it's just the rest mass energy of the electron. The electron is always there, its energy of being, it's not changing, it's just a constant energy, it's a background energy for the electron, so it can be ignored. It just sets the reference for the energy scale. Any transitions that take place do not change mc squared. Okay, so mc squared is just there. For an electron, this value is 511 kilo electron volts. Now p square over 2m is properly reflected in the Hamiltonian. This is just the classical kinetic energy of the particle. P square over 2m, so it's properly reflected. However, this term is missing and all other higher order terms are missing, which come out because of relativistic corrections. So this is a term that must be included if you would like to look at the relativistic effects on the Hamiltonian. So the Hamiltonian, the background Hamiltonian is of course H naught, plus there can be some relativistic corrections, some HR. So this HR from this binomial expansion comes out to be the operator raised to power 4, 8, m2 c squared. Okay. Now this is a perturbative Hamiltonian. We would like to see how does this relativistic Hamiltonian affect the energy eigenvalues E and naught, and how does it affect the eigenstates. But it's easier to look at the energy eigenvalues. Alright. So first of all, we notice that the if we take a ground state NLML, is this degenerate? Is there some degeneracy in these states? The states degenerate.
So sorry, N value is the
same value of N, all the, no matter what L you have, whatever Mn you have, all of them will have the same energy given by E and naught. Because the energy is only depending upon N. Right? So within each N, there is a subspace of states which is a degenerate subspace. Okay? And the level of degeneracy is 2n squared if you include the spin. So these states are 2n squared fold degenerate in the N subspace. Okay, because all of them have the same energies En. Now what we would like to see, if we were to apply a degenerate perturbation theory, we know that, how does degenerate perturbation theory work? You write down the perturbative Hamiltonian in the degenerate subspace in some basis of the degenerate subspace. For example, if your degenerate states are given by psi n j psi n I, you form a matrix comprising these elements, where n denotes the subspace, is a label for the subspace, and I and j are individual vectors, texts inside that subspace. Then you construct this matrix HP. Okay, you construct this matrix HP which comprises these elements. Then you find the eigenvalues of this perturbative Hamiltonian. The eigenvalues of this perturbative Hamiltonian will be simply be the first order energy corrections. Okay, so you write your perturbative Hamiltonian in the degenerate subspace and find its eigenvalues. You diagonalize this matrix then. And then find its eigen, which means you find its eigenvalues. The eigenvalues will be the corrections to the first order corrections. Okay. You have degenerate perturbation theory. Now we would like to apply degenerate perturbation theory. Now one beauty of several problems is that if the perturbative Hamiltonian is diagonal in the degenerate subspace, then you don't need to diagonalize. If it's already diagonal, then you don't need to diagonalize. It means that the diagonal elements of that matrix will automatically give you the energy corrections. And when will it be diagonal? It will be diagonal when the vectors in the degenerate subspace are already eigenvectors of the perturbative Hamiltonian. And when will that happen? That will happen when this perturbative Hamiltonian commutes with the background Hamiltonian in the D-unit subspace. Okay. Now, because two operators that mutually commute, they have a common eigenbasis. You can find a common eigenbasis for those operators. Now, if you look at the Hamiltonian H0, the Hamiltonian has an L square term and a PR square term and a VR, or it has a P square over 2m and a VR. Now, if you look at the relativistic Hamiltonian, which comprises a P4, now this is a homework problem that first of all you will notice that the P, which is just a vector operator, it has Px, Py, Pz, it commutes with H0. Okay, this commutes. P squared also commutes with H0. You'll find that P4 also commutes with H0. Okay. Now, if P4, this operator, commutes with H0, then you can find a set of states that are eigenstates simultaneously with H0 and P4. So, if N, L, and L are eigenstates of H0, they must also be eigenstates of P4. Because both of these operators mutually commute. Now, if you would like to prove this, you would like to prove that P square commutes with P square. Of course, it commutes with P square, and you would also like to prove that P square commutes with L square. This is something that probably you already did in the homework. You took the elements of P, you took the elements of L square in the Cartesian coordinates and found out explicitly that this commutator is 0. So if this is 0, then this must be true. If this is true, then this must be true. Because you can expand P4 as, write this as P square, and then explicitly work out the commutator, this can be 0. So if N, L, M, L are eigenstates of H0, then luckily, just out of luck, these are also eigenstates of P4. Because these operators mutually commute. Okay. So our problem of applying degenerate perturbation theory is simplified because we've already found out a set of states which are eigenstates of P4. So you will apply degenerate perturbation theory exactly in the same way as you would apply non-degenerate perturbation theory. You will find the matrix elements and only the diagonal matrix elements will be non-zero. So the corrections to the relativistic corrections to the energy E n due to the relativistic effects, first order. Okay, these are simply HR N L M N N L M N. Okay, so these energy, these are the energy corrections. Okay, now let's find out these energy corrections. The relativistic Hamiltonian is 1 over 8 m cubed c squared n l n l t 4 n l n. ठीक है? अच्छा, ये relativistic energy correction. अब this is really difficult to find out. So what we would like to do is we would like to make play a small trick. We would like to do the following. We know that H naught is P squared over 2m plus VR. So we would like to write this P squared as H naught minus VR into 2m. Okay. This means that our P4 is simply the square of the 4m squared H naught squared plus VR squared minus H naught VR minus V R H naught, right? This is my P4. Now I insert this P4, this operator is replaced by these operators and it's inserted into this. Okay, so I get the relativistic corrections to the energy first order. These are simply minus 4m squared, 1 over 2mc squared, n h naught squared, n plus b squared r. Minus n h v r Okay. Now this simply is simply E n naught squared. This is plus E squared 4 pi epsilon naught, because potentiality is minus E square over 4 pi epsilon naught R squared 1 over R squared, the expectation value 1 over R squared. Okay, in the state n. And this becomes, so you have this becomes En naught, because this is an eigenstate of H naught with a VR. VR is minus E square over 4 pi epsilon naught, expectation value of 1 over R. And you get the same term from here, so you get 2 here. उसको देखो ना माइनस ई स्क्वायर और 4 पाई एप्सिलॉन नॉट का स्क्वायर ले लीजिए
माइनस एन एल एन में
ये वाला
माइनस तो फिर ये जब हम लोग माइनस डालेंगे तो प्लस आ जाएगा.
Now these expectation values, right, 1 over r squared, 1 over r, these are the expectation values of a position coordinate, 1 over r squared, this is expectation value 1 over r. So you know what the wave, you know the general form of the wave function. You can compute this explicitly by integration, by straightforward integration, or you could apply the virial theorem. Did you study the virial theorem in recitation? No. You can just put in these values. For example, if you would like to find expectation value of 1 over r, you will have 1 over r. Since you're talking about radial probability distribution, 4 pi r squared, 1 over r into r n l function r modulus squared dr minus infinity to plus infinity. This will give you the expectation value of 1 over r. Okay. Now, I don't expect you to do this, but it's actually quite straightforward to construct this integral and solve it, but there are single ways of doing it. So I will just state the results. The results are the following.
इधर हम Rn चलेंगे, that will be Rn naught, जो हमें उसके लिए H naught में था, या Rn चेंज हो जाएगा?
Given R,
कैपिटल R, yes.
ये रेडियल वेव फंक्शन है जो unperturbed states, unperturbed state. क्योंकि स्टेट तो वही आप कंसीडर कर रहे हैं ना. फर्स्ट ऑर्डर टर्म इन द perturbation theory, you take the unperturbed value, you take the expectation value of the perturbative Hamiltonian in the unperturbed states. Alright, so the expectation value of 1 over R is 1 over m squared A naught, where A naught is the Bohr radius and A naught is given by 4 pi epsilon naught h bar squared over 4 by epsilon naught h bar squared over m squared. This is the Bohr radius. Okay. 1 over r squared, its expectation value is given by 1 over n cube a naught squared L plus half. Now if you plug in all of these values, the relativistic corrections to the energies to the first order come out as minus mc squared alpha is to power 4 divided by 8n raised to power 4 4n n plus half minus 3. Important result. Now it's a long tedious algebra. I can do it, which means you can also do it. It's not a big problem. Just takes half an hour away from Facebook. I think you should do this calculation. You just take these perturbative terms, plug in the values for the expectation values and see if you can get this relativistic correction. Now what is the most striking result of this? There are 2 or 3 most striking results in this correction term. आप इस correction term क्या चीज ज़्यादा strike करती है?
L आ गया,
L आ गया पहली बार. तो first of all our energy, our coulombic energy, the unperturbed energies were independent of L. Now what we have is that the energies depend upon L. For the same value of n, whatever the value of L or M, all these states were previously degenerate. But now the introduction of the relativistic term has conferred upon the energies a dependence upon L. So the energies are no longer dependent upon just n, they depend upon L as well. What this relativistic correction done, it has lifted the degeneracy. हम इसकी पहले भी examples देखेंगे, जब perturbation होती है तो degeneracy is lifted. So the degeneracy is lifted by dint of this relativistic connection. The second point is that if you look at the unperturbed energies, these energies, these are proportional to alpha squared, whereas these relativistic corrections are proportional to alpha 4. So the relativistic corrections are alpha squared times smaller than the coulombic energies. Okay. So there are 2 kinds of interactions at this scale. One is a relativistic correction. The other is the spin orbit interaction. Let's spend a few moments on the spin orbit interaction. And remember, just remember, we're looking at the most simplest atom of the periodic table, hydrogen. We're not even looking at one of its isotopes. just hydrogen, and the level of complication is beautiful and it's quite involved at the same time. So expecting quantum mechanics to give you analytical results for anything beyond helium perhaps is just totally out of question. But it does give you a handle on how to tackle these problems. It gives you approximate results. If you can solve them analytically, the exact results will be exact. Okay? So just see how nature would like to censor itself, how nature would like to hide itself from us. But quantum mechanics is keen behind it and trying to capture it. And it successfully does in many cases. So this is the relativistic correction only to the first order. Now you also have these Rydberg atoms. Rydberg atoms which just, for example, look at the alkali metals. One electron in the valence shell. Okay? And so that one electron in the valence shell acts like a hydrogen-like atom. But then again it's very complicated to solve the energy states for that atom exactly. Okay, so now let's spend some time on the spin-orbit interaction. And the spin-orbit interaction gives a beautiful view of the addition of angular momentum. You've already looked at the spin-orbit interaction, I think, not in extraordinary detail, but you already have an idea of what the spin-orbit interaction is. The spin-orbit interaction basically is that if you have an electron with a certain orbital angular momentum L, it will, of course, it has a spin half. So this L and S will add up to give you total angular momentum, which is given by L plus half or L minus half. Okay, angular momentums will add. Okay, and you can form coupled and uncoupled basis. Remember that this L minus half only exists when L is greater than 0. If L is 0, you cannot have an L minus half. Okay, so so the origin of the spin-orbit interaction is quite simple. If you have a proton and if you have an electron, the electron is going around the proton. From the electron's rest frame, it's the proton that's going around the electron. So this is a revolving charge and will produce a magnetic field here. Okay, now the electron itself is a magnetic moment, so its magnetic moment will interact with the magnetic field. It will have a certain energy. That's the energy of the dipole inside the magnetic field. So the spin-orbit interaction is, and then there are certain relativistic corrections to this as well, because we have non-inertial frame. The spin-orbit interaction turns out to be equal to E squared over 8 pi m squared c squared epsilon naught r2 s dotted with L. Now the sequence of affairs is the following. You find the magnetic field due to this revolving proton B. You know its distance is r. You know its charge, so you can find out what the current is. From the current, you can find out what the magnetic field at the center of a current carrying loop is. You study that in electricity and magnetism. You find out that magnetic field, and then you have the spin, the magnetic moment of the proton interacting with the magnetic field. This is the Hamiltonian for the system. This is the spin-orbit interaction Hamiltonian. Now the magnetic moment for the electron is given by GE over E over 2m, where m is the mass of the electron, S. Right? Where G is the lambda G factor for the electron, which has a value of 2. And B will be proportional to L. This B will be proportional to L. Right? This is a simple calculation that you should be able to do on your own. Okay, because V is proportional to the velocity is proportional to the angular momentum. Okay, so this is the final spin-orbit interaction that comes out. I'll probably give one question in the homework for this. So there is an effective magnetic field that the electron is seeing here. because of its own revolution around the proton. Okay, which means that the spin of the electron is being coupled to the angular momentum, orbital angular momentum of the electron. Now, if you remember the spin-orbit interaction, we also had a Hamiltonian of this kind, an interaction Hamiltonian. With this was S1, this was S2, and we would form eigenstates of this Hamiltonian, which would represent the coupled basis, which are also called the coupled basis states. Right? Now, exactly the same problem now reappears. We have the spin-orbit interaction, we have the unperturbed Hamiltonian, and on top of this we have the spin-orbit interaction, S0. And we also have the relativistic interaction. This is now our fine structure Hamiltonian. Now, the relativistic interaction is a p photon, it commutes with everything else. So you can find the corrections to this energy separately, and you can find the corrections of rendered by this perturbation separately. So we would like to find out the corrections to this energy separately. Now, once again, we have the same problem. The problem that we have now is that the energy levels are degenerate in the n-fold subspace. So we would like to apply degenerate perturbation here. ठीक है? अच्छा. ठीक हो गया? अब आप ये देखें कि let's look at this Hamiltonian H S0. H S0, it commutes L squared. It's an interaction Hamiltonian. जिस तरह hyperfine interaction याद करें, वो किसी एक angular momentum के magnitude, किसी एक particle के angular momentum के magnitude को commute करता है. ठीक है? It also commutes with S squared. Does HS0 commute with LZ? Do these commute? No, it doesn't. It does not commute with the Z component of either one of the angular momentum, of a component of any one angular momentum. Neither does it commute with SZ. This commutator is not zero. This is not zero. No reason why. L squared is LZ squared plus LX squared plus L plus Ly squared. Right? It does not commute with LZ. You have two spins that are interacting by a Hamiltonian. Now, there is no external torque acting. The torque is coming from the interaction on each individual spin. What the torque can do is that it can rotate the magnetic moment of one of the particles. So, this means that the angular momentum of either of these particles is only rotated in space. So, its magnitude must remain constant. However, its projection along any one of the axes is not conserved. Okay. Okay. And what can we say about J squared? Does HS not commute with J squared? Yes, it does. This is the total angular momentum. It also commutes with JZ. Okay. So it commutes with the total angular momentum. So if you were to write the set of commuting set of compatible set of commuting observables, we have HS naught. We have J squared, we have JZ, we have L squared, and we have S squared. Alright. This also means that M, L, S, M, L, M, S. Now this is just the uncoupled basis, isn't it? This is simply a shorthand writing ML cancelled with NMS. Right? So this is the orbital degree of freedom, this is the spin degree of freedom. MS. So HS, these states, these direct product states, or the uncoupled states, the direct product states are not eigenstates of HS naught, because HS naught does not commute with LZ or SZ. So these states are eigenstates of LZ and SZ. So HS naught, if you would like to, we know that these direct uncoupled states are not eigenstates of HS naught. However, states of this kind, N, L, S, J and J will indeed be eigenstates of HS naught, because these states are simultaneous eigenstates of all of these operators. Okay? So what we've done is that we would like to apply these and perturbation theories, and we've already found out the eigenstates of the perturbative Hamiltonian. Okay? And we know that this J is constrained to be L plus half or L minus half. So once we have found out the eigenstates of the perturbative Hamiltonian, writing it in the degenerate subspace becomes really easy, because it becomes diagonal in the degenerate subspace. So the problem of diagonalization of the perturbative Hamiltonian in the degenerate subspace is bypassed by finding out the eigenstates of the perturbative Hamiltonian. Right? So the corrections to the energy will simply be given by to the nth level due to the spin orbit interaction. To first order, they will be given by N, L, S, J. I am not writing the MJ because it does not matter here. HS naught, N, L, S, J. Now these are eigenstates of HS naught. So I have already diagonalized the perturbative Hamiltonian because I found out the eigenstates. Okay, so I used my knowledge of angular momentum commutation relationship to find out the eigenstates of the spin orbit interaction. Now if I look at this, now what do I have here? Here I have HS naught is given by this S dot L. So I have E squared over 8 pi M squared C squared epsilon naught, not of course, S dot into L N L S J over R2 here N L S J. Now these are indeed eigenstates of S dot L, because these are states in the coupled basis, and they are eigenstates of this interaction. Just like the spin orbit interaction, the hyperfine interaction. If I have S1, S2 here, then I have N, L, S total, which is an eigenstate of S dot L, of S1 dot S2. Okay. Now if I would like to compute this, I once again play a trick. I have J squared is S plus L squared. This is S squared plus L squared. Does L come into this? Yes, they do, because they act on different particles. I mean, they act on different degrees of freedom of the same particle. L dot S. Okay. This means that my L dot S can also be written as J squared minus S squared minus L squared divided by 2. So I replace this prescription for S dot L into this. And what do I get? I straight away get these spin orbit corrections to the energy which I get. E squared over A by N squared C squared epsilon naught number 2. Now j squared, I get h bar squared. I get j plus 1 minus s into s plus 1 minus l squared minus l plus 1, and the expectation value 1 over r2. अब ये s into s minus 1 is basically 3 by 4 for a spin half particle such as an electron. Okay. Now I can find out the value of 1 over r cube. Alright, let's just put this in. These ones by explicit integration or by the real thing. I'll probably give you homework for this. Okay, and if I then plug in these values, I get En spin orbit interaction first order is simply n c squared alpha 4 nu j plus 1 minus l plus 1 minus 3 by 4 l plus 1 l plus half. So these are the spin orbit corrections to the first order due to the spin orbit interaction. Again, you notice that there is an alpha 4 dependence. So these corrections are of the same order as the relativistic corrections. And then I can add up both of these corrections because H are commutes with the spin orbit interaction. I can add up both of these corrections and observe something really interesting. Alright, one thing I would like to point out is the following. If L is 0, you look at this term, what will this term be equal to? Undefined. I mean it's infinity. So this correction, so this is not going to work for L equals 0. However, you notice that if you have L equals 0, then what is HS naught? What is this term? 0. So if you have an electron in an s orbital, there is no spin orbit interaction. Okay? And this formula comes out to be correct if you apply the Dirac's equation. So this formula as it applies here is not valid for L equals 0. So this formula is only valid for L greater than 0, for the p orbital, d orbital, or f orbital. For there is no spin orbit interaction for an electron in an s orbital. However, there is a relativistic interaction. Now, if I add up these corrections to the first order, E, N, L, again I notice a dependence upon L. And J, a dependence upon L also leaks into a dependence upon J, because J equals L plus half or L minus half. So you can either write L or J, it doesn't matter. Okay. So the first order correction due to both of these are really relativistic effects. One is the relativistic correction to the energy, the second is the spin-orbit interaction, which is in itself a relativistic effect because it includes relative velocity between the electron and the proton. So both of these corrections can be added to give you a total sum. Total sum, and this correction is given by, so this is long algebra. I can do it, you can do it. That's the rule. This turns out to be minus mc squared alpha 4 divided by 2n cube 1 over j plus half minus 3 over 4n. Now if you look at this formula, I will express this in terms of n and j. Now this is a miraculous formula because if you work out the algebra, first of all, it applies for j equals L plus half and it also applies for j equals L minus half. You get the same formula. So this j can be L plus half or L minus half. You plug in the values of L, replace them by j minus half or j plus half, you get the same formula. So this is a really general formula for both values of j. Second, its formula is also valid for L equals 0. Because when L equals 0, this term is 0 and all of this reproduces the relativistic energy correction when L equals 0. So this formula is valid for any L, for any n, for any j. Okay? So I give you,
So we got this by adding HR and E and S O. By adding these two methods.
Yeah, because they mutually commute, so you can find the corrections for either one of them and add the corrections. So these are called the fine structure corrections to the energy. And let's draw an energy manifold and see what's happening graphically. If you look at these fine structure corrections, it's again alpha squared smaller than the Coulombic energies. Because the Coulombic energy depends on alpha squared, this depends on alpha 4. And it has a dependence upon n as well as j. What the spin orbit interaction and the relativistic correction done, it has lifted the degeneracy to n subspace. Now you have states with the same value of n and j with the same energy. And ml and ms are no longer good quantum numbers, they are bad quantum numbers. You cannot talk about ml and ms any longer. Because SL does not commute, SZ does not commute with the perturbative number. LZ does not commute with the perturbative number. So ml and ms lose meaning at all. They have no meaning at all if you include the spin orbit interaction. They are bad quantum numbers. The good quantum numbers are n, l, s, j, and if need arises mj, which is the z component of the total angular momentum. So you can only talk about the total angular momentum or the individual angular momentum's magnitude, but not the individual components of the individual angular momentums. Okay, they become bad quantum numbers. So this is the entire machinery of addition of angular momentum. Now let's see what's happening graphically in the energy diagram.
So you said that this formula works even for L equals to 0. But if you put L equals to 0, J equals to half, and the En realistic and Enj, won't they be different then?
L equals 0.
J equals to half or minus half?
J equals half, cannot be negative.
J equals to half.
Yeah.
And that would change the value that we are getting here and here. Right? Because if we put L equals to 0 here, it only gives us 4n over half minus 3. Here we are getting 4n over 2 minus 3. If we take 4n out common. For n over 1 side.
4n over half is 8n.
Here it will be half plus half. Here it will be only half. That's what I am saying. 4n divided by half for L equals to 0 here. For there it will be 4n divided by half plus half. because there will be the S part contributing.
मैंने ये मैच किया है अच्छा अगर मैं यहाँ इस फॉर्मूले को मैं एक मिनट अगर मैं यहाँ j इक्वल्स हाफ कर दूँ ठीक है which means l equals 0 yes ठीक है तो ये होगा minus mc square alpha 4 2m cube half plus half is 1 minus 1 minus 3 over 4m right
Yes, sir.
I take 4m common minus mc square alpha 4 8m4 right
Yes, sir.
I get 4m common 4m minus 3
Yes.
ऐसे ही है ना यहाँ देखो
4n
minus m c square alpha 4 8m4 I get L is 0
Yes, sir.
8m minus 3 ठीक है
Good.
probably there's an 8 here right there's an 8 here this formula would match so one has to do the calculation probably there's an 8 here
Would you be at 2?
I think चला जाएगा ना
यहाँ 4n ही आएगा वहाँ शायद
हाँ
change
2n क्योंकि L 0 होगा ये हाफ ऊपर चल के 4n हो जाएगा 2n ठीक है अच्छा अब हमें क्या देखना है क्या बात करके हाँ we would like to draw a fine structure let's look at the coulombic energies first we have 1s okay then we have 2s 2p 2s both of these levels have the same energy because they have the same value of n okay then we have 3s 3p 3d all three of them have the same energy because they have the same value of n this energy is minus 13.6 electron volt this is minus 10 electron volt and so on this is minus 13.6 divided by 4 but this is about minus 2 electron volt perhaps this is minus 13.6 divided by 8 okay because it is a 1 over n square dependence so these are the unperturbed energies okay now this is two-fold degenerated n is 1 so two levels correspond to spin plus and spin half and spin minus half so 2s and 2p they are 8-fold degenerated n squared is 4 8-fold degenerated 2s is just 1-fold degenerated 2p is 3-fold degenerated so 4 levels but you do spin get 8 correct likewise you can find out this is 3 squared 9 18-fold this is an 18-fold degenerate if you include spin now these are the degenerate subspaces n equals 2 gives a degenerate subspace n equals 3 gives a degenerate subspace now you would like to apply the spin orbit and the relativistic corrections now if you have 1s now 1s corresponds to a value of j given by 1/2 so this level is going to shift down if you put j equals 1/2 here n equals 1 this level is going to shift down by some value. Okay. Now this level is being defined by a value of j and a value of n. So I would like to call this level 1. S for this term, this symbol represents the value of L. L is 0 for this level. And I put a small half here. This value represents the value of j. Okay, so I get 1 S half. This is a 1 S half level. And this downward shift is of the order of gigahertz. Okay. Now if I look at these levels, this is the unperturbed level. I would see that 2s shifts and okay. Now 2s and 2p. Let's look at 2s first. For an s orbital, j is equal to half. It has to be half. It cannot be any other value. So 2s shifts downward. This becomes 2s half. Okay. Now for a p orbital, I have L equals 1. J can have two values, 3 by 2 and 1 half. Now for these different values of j, for the same p orbital, I get different values because the value of j is different. However, this 2s half and 2p half will be at the same energy level because both of these states have the same value of j and the same value of n. So if I look at these corrections, same value of n, same value of j gives me the same energy. So 2s half and 2p half are at the same energy level. They are degenerate states if we apply the fine structure correction. However, 2p 3 by 2 is at a different energy level. So it's slightly higher. So this energy level corresponds to 2p 3 by 2. So once the fine structure interaction is taken into account, remember that these energy splittings are of the order of electron volts. These energy splittings are of the order of micro electron volts. So I'm exaggerating this energy splitting here. These are million times smaller than these splittings. So when I apply the fine structure perturbation, these energy levels, the degeneracy is lifted, and this is the new energy manifold that appears. Likewise, if I look at these energy levels, the new energies that appear will be 3s half, okay, at the lowest energy. Then you will have 3p half. Oh sorry, इसके साथ होगा 3p half. फिर होगा 3p 3 by 2, 3d 3 by 2. Then you will have 3d 5 by 2. For example, let's look at the d orbital. D orbital means L equals 2. L equals 2 means J can take up two values, 5 by 2 and 3 by 2. L plus half and L minus half. So corresponding to D, if J is 3 by 2, it will be iso energy with the P 3 by 2 orbital. So what the fine structure correction does is that angular momentums add up to give you total angular momentum, and the energy levels are shift because of degenerate perturbation theory. And your application of degenerate perturbation theory will be simplified if you can find the eigenstates of the perturbing angular momentum.
So 3d half नहीं होगी?
3d half नहीं होगा क्योंकि d की वैल्यू सिर्फ 5 by 2 में सबसे बड़ी होगी. Remember that these symbols are called term symbols. Term symbols में यह है कि you write S, P, D, F, G, etc. for the value of L. L अगर 0 होगा, S लिखेंगे वरना P, D, F. वो कैपिटल होगा मल्टीपल इलेक्ट्रॉन सिस्टम्स. एक इलेक्ट्रॉन के लिए सिर्फ हम स्मॉल ए कैपिटल उसमें जब 2 इलेक्ट्रॉन ये ज्यादा होगा. ठीक है, इसके साथ यहाँ पे होगी 2J plus 1. और ये भी स्मॉल j इसकी सिंगल इलेक्ट्रॉन की बात करें 2j plus 1 यहाँ पे sorry और अगर स्पिन की बात होगी 2s प्लस वो मैं अभी नहीं बता रहा, यहाँ पे m, ठीक है, m, this is just a label for this level, a symbol for this level. So you have 1s half, 2p half, 2s half. These are called term symbols. Alright, so in the next lecture, which is on Wednesday, what we're going to do, we're going to take the fine structure interaction. We have this machinery built up with us. I'm going to give you another homework that's due next Monday, based upon all of this. In the next lecture, we're going to apply the magnetic field. We're going to apply a ratio Hamiltonian interaction. Now, depending upon the strength of that magnetic field, we would like to find out how do angular momentums add, what are good numbers, what are bad quantum numbers, how would these energy levels shift if we apply a magnetic field. And then in the last part of the next lecture, we'll look at how does the total J angular momentum of electron talk with the nucleus, which is a hyperfine interaction, but not between two spins, but with the total angular momentum and the nucleus. Okay, so this is the entire machinery that is being built up, which is based upon the addition of angular momentum. Alright? Inshallah, see. And the quiz today is going to take place at 12:30.